Hello, and welcome back to another video. You must remember the limit in caps. Well, today we will integrate it from 0 to infinity, and yeah, it is non-integratable. So we can't find antiderivative and solve. Well, remembering the atom bomb, I'm going to use Feynman's trick. I'm not going to prove it. Maybe for another video, let's just trust him. Remember, he was a part of the project which played an integral part in finishing the Second World War. So here is the trick. It's called differentiating under the integral sign. And let's see what it is. Alright, so here is the trick. Suppose you have a function g with the variable as t is equal to integral from a to b. It's a definite integral, that's important. And a function of x and t with respect to x, sorry. And you want to find the derivative of g of t with respect to t. That's basically g prime of t. We can write that as integral from a to b of del Okay, now this del, it might seem like a mystery to some people. A lot of people might recognize it as partial derivative. This basically means treating t as the only variable and x is a constant. Like suppose you have f of x comma t as x into t, and you want to find del f of x comma t with respect to t. So that's just, so x is basically a constant, so we can directly write it as x, cause derivative of t with respect to t is equal to 1. Okay, so that was the main idea. And now you can see why it's called differentiating under the integral, because under the integral sign you take a derivative. Okay, so we're going to be using this trick to solve this question. Okay, so how are we going to use it? Well, it's not apparent, like there is no other variable, there is only one variable x. Well, so we need a way to eliminate this x because we don't like x in the denominator. If there's a trigonometric, we prefer everything to be trigonometric, or if there's like a polynomial, we prefer everything to be polynomial. We don't like it when these two are mixed up because it makes things tough for us. So we want this x to be eliminated. So, well, we can assume another function g of t. Oh, sorry, I forgot to write the limits. Oh, this t, that's fine. Well, now why do we take this? Because if you differentiate this with respect to t and we take the differential under this integral, the x comes out, x is a constant, so it comes out like if you take e to the power 2x, over here 2 is the constant, take and differentiate it, 2 comes out and you get e to the power 2x. And now you can, and e to the power some variable in terms of x into sine x is good because we can easily use integration by parts. And well, so we can, let's see how that works. So we have g prime of t is equal to integral 0 to infinity and sine x by x, because this does not have any t term, so it's basically a constant with respect to t, so we can ignore this. And this thing comes out to be minus x into e to the power minus tx dx. And like magic, these two cut out, these two cancel out, whichever you prefer it. And that's integral 0 to infinity sine x minus sine x into e to the power minus tx dx. And we can solve for this. Okay, so for this I'll just use the DI method, which I've already talked about in the factorial video where I find pi factorial. Well, you can take either of these because these both, well, in some form or shape tend to be periodic in derivatives, because e to the power tx will just turn to be t into e to the power tx and t square, and sine x will keep on rotating with cos x with interchange of signs. So either will be fine. I'll take sine. I'll take e to the power minus tx over here, minus e to the power minus tx, so this one is accounted for. And this one I'll take sin x. I took this because I prefer t's in the numerator, not in the denominator. And then this will give t into e to the power minus tx and minus t square e to the power minus tx. This one is minus cos x, and this one is minus sin x. Plus minus plus. And I'll name this one I. So we have I is equal to cos x into e to the power minus tx plus sin x t e to the power minus tx, and for this one plus t square. Wait a minute, 1 second. That gives plus and plus, so that we want a minus, so t square into minus I. So now we have t square plus 1 into I is equal to, well, this big thing over here with the limits from 0 to infinity. So I'll put the limits and directly put the value over here. So at cos at infinity we have no idea, but it's between minus 1 and 1. And e to the power minus tx, where x tends to infinity, is 0, so that doesn't matter. So 0 minus cos at x is equal to 0 is 1, and this is also 1, so that's fine. And for this, same thing for sine, we have no idea what is at infinity, but t by e to the power tx at x tends to infinity is 0, so plus 0 minus 0. So we get I is equal to minus 1 by t square plus 1, and we have I is equal to g prime of t is equal to minus 1 by t square plus 1. So if you take the antiderivative of this, which this is a very easy function to anti-differentiate, so we get g of t is equal to minus tan inverse of t plus c. Now we don't know what this c is, so if we get the c, we get the answer by putting t is equal to 0, because if you put t is equal to 0 over here, over here, if we put t is equal to 0 over here, we get sin x by x dx. So we need, and now if you see, if you put t is equal to infinity, the inner value just goes to 0, and integral of 0 dx is 0, because that's just a straight line on the x-axis and there is no area under it. So we know one more thing, we know that g of infinity is equal to 0. So we can, and we also know g of infinity is c minus tan inverse of infinity is equal to 0. So c is equal to pi by 2. And now our answer which we are looking for is equal to g of 0. So g of 0, well, tan inverse of minus tan inverse of 0 is 0. So g of 0 is c. So the final answer, integral of sin x by x dx from 0 to infinity is equal to pi by 2. And this is an amazing answer. This is one of the most perfect answers which this question could have. And these questions are exactly why maths is fun and why you should subscribe to my channel. Please like, share and comment on my video, and subscribe to my channel for more such cool stuff.